This is the tutorial for the analysis at seismic resolution of SeisRP. The module creates the depth to time relationship and displays a pre-stack synthetic seismogram and attributes in two-way time at seismic resolution. The depth to time relationship is obtained by integrating the sonic log and displacing the integrated curve, a time computed using the user-defined or user-supplied replacement velocity. In this case, we see that the sonic velocity is about 4,000 meters per second, and we're going to change the replacement velocity to be 3,000 meters per second. When we do this, we observe that if we have the replacement velocity at 2,000 meters per second, the pre-stack synthetic seismogram and attributes would be plotted in a range from 3 to 3.2 seconds, whereas changing the replacement velocity to 3,000 meters per second, the pre-stack synthetic seismogram and attributes will be plotted from 2 to 2.2 seconds. The second track is the QC of the interpolation done in the depth to time curve generation. It shows three curves. The blue curve is the sonic velocity log. The orange curve, which overlays very closely the blue curve, is the sonic velocity interpolated to the processing sampling interval, which is 1/10 of a millisecond and then displayed in depth. And finally, the yellow curve, which does not follow the other two curves, is the sonic velocity sampled to the user-defined interval, in this case 1 millisecond, and also displayed in depth. If we set the user-supplied sampling interval to 1/10 of a millisecond, which is the processing sampling interval, we see that the three curves overlay each other. Let's now do some pre-stack synthetic seismograms. This is the template for the synthetic gather generation, or the synthetic data. The first track shows the same information that we were seeing in the previous plot, the sampling QC. In this case, it's plotted in two-way time. The second track are the attributes, let's say, and which are selected in this green box. Let's say that we wanted to do, instead of lambda of normal incidence and gradient, we wanted to do relative lambda rho and relative mu rho. This is what we would get. So in the left we have normal incidence and gradient, and in the right we have relative lambda rho and relative mu rho. Let me go back to normal incidence and gradient, since they are going to be the reference attributes for all the plots. The second row here in the pink box indicates the angle range in which the angle gather is going to be generated. In this case, it's going to be from 0 to 45 degrees every 1 degree, as annotated down here. Let's say that we wanted to plot or to create the pre-stack synthetic from 10 degrees to 30 degrees, incrementing by 1 degree. Do the pre-stack synthetic, and this is what we would see. Here we now have the pre-stack synthetic done from 10 to 30 degrees, which would actually be a subset of the plot here in the left. The display limits, in this case 0.2, as shown in here, minus 0.2 to 0.2, are used to change the gain of the plot. Let's say that we wanted to create this plot at a higher gain. We will then go to 0.1 display limits and redisplay it, and then now we have higher gain because the display limits are minus zero point 0.1 to 0.1. Let's now go to the scatter plot, and let's do the scatter plot from minus zero point 0.4 to zero point 0.4 in both x and y. This is the scatter plot of normal incidence and gradient, the attributes displayed in the second track. This anomaly looks very extended in the second and the four quadrants, and it happens that it's very affected by tuning. In another clip, in clip number 2, the shape of this anomaly is further investigated. The magenta points in here are the points corresponding to the target. In here we can select a line and get a blue point in the scatter plot, or use mouse button 3 and get a red point in the scatter plot. So mouse button 1 creates a blue point and a blue line, mouse button 3 creates a red line and a red point, mouse button 2 erase the lines and the points. The same can be done from the scatter plot. Select the point, maps back to the seismic, mouse button 1 and mouse button 3 creates a red point and a red line, mouse button 2 deletes the points. I'm going to ask you to pay attention to these numbers down in here in the AVO. They correspond to the times in which we select the lines and the points, and they are also the times at which the AVO plots are going to be created. So we can come in here, mouse button 1 in the lowest value of normal incidence, and then mouse button 3 in the highest value of normal incidence, and do the AVO plot. This would be the AVO plot. I'm going to keep this for comparison in just a minute. I'm going to use these same plots to do the comparison with the Sopritz equations. So we're now going to create the pre-stack synthetic gather using the Sopritz equations. That's it. We see some differences, especially in the part traces as expected. Let's now do the AVO plot. So what we see here in the left, we see the pre-stack synthetic with Akin-Richards equations and the AVO plot with the Akin-Richards, and in the right the pre-stack synthetic and attributes using Sopritz equation. Let's now go to the wavelet box. Here is where we're going to define the wavelet. In this case we're using a 5, 12, 50, 75 Hz Ormsby wavelet. Let's say that we wanted to see how a 100 to 150 Hz Ormsby wavelet would look. And this is how the AVO attributes and the pre-stack synthetics could look if the upper limits of the Ormsby filter were 100 to 150 Hz. We can also have a Ricker wavelet, in this case 25 Hz Ricker, or we may choose to not use a wavelet. In this case it's going to be a spike with the filter, anti-alias filter of 1 millisecond. The wavelet QC is exactly what it says, a way to QC the wavelet. Here we have a normal speed wavelet 512, 50 to 75. Let's say that we wanted to plot from a minus 100 mils to 100 mils and 100 hertz, up to 100 hertz. The plot, and we can also integrate the wavelet. In this case, we see that the integrated wavelet would have a 90 degrees phase shift, and we have a higher amplitude in the low frequencies, and the wavelet would be anti-symmetric. And with the other point, or the other QC that we're missing, are the general parameters. These are common to more than one module, and they will be covered in another tutorial. Thank you.